So let's see. I want to finish up the ionization of hydrogen, and then say something about the kind of quantized electromagnetic field that's generated by a classical current, and then maybe I'll do that in third place. In second place, I want to describe or summarize something we learned about emission and absorption of light by atoms, and then and that will lead us. That will give us a derivation of the Bose-Einstein curve, which I guess is exact. And then that, by the way, is the curve that's observed in the background radiation, cosmic microwave background radiation. And then after that, I want to discuss the scattering of a photon by an atom, and I don't think we're going to get through that, but I can say a few words about it. Okay, so that's the plan. Let me find my notes here on ionization of hydrogen. Let me just make sure I've got that going.
Are you able to model?
Say that again?
Are you able to model like molecular, not atomic hydrogen, but like hydrogen gas? You know,
oh, you mean molecular hydrogen?
Yeah, molecular hydrogen.
Gosh, I mean, this is not.
The ionization energy changes a little bit, doesn't it?
Yeah, I imagine so. I'm just discussing atomic hydrogen. I have to think in order to generalize it to molecular hydrogen. So what's the story? Out in space, there are regions of just atomic hydrogen, aren't there? But are those already ionized, or is it?
I don't really know.
Okay. Well, I want to go through this ionization thing somewhat quickly, because we've already talked about it a couple of times, and we just didn't have enough time to finish. This matrix element is minus I over h bar equals 0 to t. As usual, the free Hamiltonians on both sides pull out the energies, and what we have is e to the I EP minus E, let me just say G as ground state, minus h bar omega t prime over h bar t prime, and all that multiplies a matrix element, which is minus q over m p dot epsilon, and simply a and 1, 0, 0 k. Okay. Equals sign. And so altogether, that's IQ over h bar m. The matrix element gives us just, after all, we just have an annihilation operator here. There's only one photon, so we just get p dot epsilon, and then we have that square root of h bar over 2. We get this, epsilon z 0 b k, and finally we have P E-T-I K dot X 100. We've gotten rid of K, and the time integral here is e to the I. Let me just call it delta ET minus 1 over delta E. But when we do that, we cancel the I over H bar. So this is our expression. What's this matrix element? Well, P EBI K dot X 100. I might have missed. I think I missed a factor of 2 in this because I was converting from. Well, I was trying to do it really on the fly, although I had noticed that there were other units. So it's 4 square root of pi over b, z over a0 to the 3/2, 2 z a0 cubed over z squared plus, and I'm calling this s squared a0 squared, and s here I'm taking to be the initial photon wave vector minus the wave vector of the emitted electron. So that's what happened. You remember we insert a complete set of states, and I think I went through this part last time. I think there was a factor of 2 missing. In any event, when we put this together, what we get is PST0 100K squared is 4Q squared over M squared sine squared of delta E T over 2H bar divided by delta E squared, and then times the matrix element. Oh gosh, I'm almost going backwards here because I've gotten back to P dot A 100K squared, so that's sort of going backwards. Let me say, this turns into a delta function. So this is 4Q squared over M squared, the matrix element P dot A 100K squared delta of delta E times 5T over 2H1. And altogether, when we put these things together, we get that the rate apart from final states is Q squared pi over M squared H bar over epsilon 0 B omega K P dot epsilon R of K squared 16 pi over V Z over A0 cubed 4Z squared A0 to the 6th over Z squared plus, this is S squared, A0 squared to the 4th. And then finally, this delta of delta E, which you remember is EP minus EG minus H bar omega K. So that's that expression, and of course EP is P squared over 2M, so dE of P is P over M dP, sorry. P over M dP, and the sum over these final states it's not simply V over 2 pi h bar cubed d cubed p, but there's a factor of 2 here because the final electron can have 2 possible spin states. And we're not measuring them, we're just summing over them. And so this is 2v p squared dp d omega over 2 pi h bar cubed. And so the total rate is 2v over 2 pi h bar cubed integral p squared dp d omega w hat, which is 2vm over 2 pi h bar cubed integral p de of p d omega w hat. Well, the dE, the reason for going to dE of p is that then you can do the delta function without worrying about the scaling factor. And when you put all this together, what you get is 32 q squared pi squared p dot epsilon r of k squared divided by m 2 pi h bar, that's a cube. Cubed epsilon 0 v omega k z over a0 cubed 4z squared a0, this is the Bohr radius to the 6, z squared plus s squared a0 squared to the 4th, and then d omega. Okay. Any questions? I still have chocolate, but I'm running very low on chocolate. Enough for today. If I get 3 questions, I can survive today. I remember to bring the crackers. Okay, so this is the expression, and as I mentioned to you last time, well, there are 2 possibilities. One possibility is that we have an unpolarized beam of photons. And if we have an unpolarized beam of photons, then what we have to do is we have to average this sum. So we average the sum over R of p dot epsilon R of k squared. And so this is 1/2 p, I need the sum sign. Sum R equals 1 to 2. P dot epsilon R of k, epsilon R dagger of k dot p. So that makes that thing into a matrix. And if you now maybe I should do this more explicitly. Let me do this more explicitly for you, just in case people have a hard time with this. This is saying pi epsilon ri epsilon rj star pj. Okay. So it's this guy is sort of a row vector here. This thing is a matrix, and this guy is a column vector. And this matrix is the outer product matrix. And the way you do such an outer product matrix is you just take the vector like that, epsilon I, and then the vector epsilon j star like that, and then you multiply all the elements of this column times all the elements of this row, and you just make a matrix that's 3 by 3. Okay? So that's how that works. And that particular matrix is it's the identity operator minus the projection operator on the vector k, because the polarization vectors have to be orthogonal to k. So this particular matrix in here, in other words, we get down to here, 1/2 sum epsilon r of k dot p squared then is 1/2, and now let me just sort of look at notes. P on the left, the matrix is I minus k hat transpose P, and that is equal to 1/2 P squared minus P dot K squared, which is 1/2 P squared times 1 minus cosine squared theta. And here, the angle between P and K is cosine theta. Okay, so in fact, I'm going to use this later, so let me draw a picture. We've got this as K, suppose that is in the z-axis. The ejected momentum of the electron is P angle theta. This is the x-axis, that's the y-axis. And you drop this perpendicular and you have an angle P here. Okay. So that's our picture. Theta and phi are the polar angles of the ejected electron. But only cosine squared comes in here, and this is in fact 1/2 P squared sine squared of theta. Okay, the initial flux F is the number of photons in the state times C over V, but we've got n equals 1 here, so it's just C over V. So we divide the rate W by C over V, and that gives us d sigma d omega is W over F, which is WV over C, and this turns out to be 64 pi squared Q squared V over C M 2 pi H bar cubed Z over A0 cubed Z squared A0 to the 6th P cubed sine squared theta divided by epsilon 0 V omega K Z squared plus S squared A0 squared to the 4th power. And obviously that can be collapsed somewhat. First of all to 8 Z to the 5th A0 cubed Q squared over M pi H bar cubed C epsilon 0 C, let's say, omega K P cubed sine squared theta over Z squared plus S squared 0 squared to the 4th. Now you remember Q squared in SI units is 4 pi epsilon 0. The fine structure constant alpha, which is 1 over 137, H bar C. And so when we put that in, what we get is 8 z to the 5th a0 cubed 4 pi epsilon 0 alpha h bar c over m pi h bar cubed c epsilon 0 omega k p cubed sine squared theta over z squared plus s squared a0 squared 4. By the way, all these occurrences of h bar and c, not to mention epsilon 0 and occasionally mu 0, are what prompted Feynman in particular to, I don't know if he invented natural units, but he certainly promoted them. And when you're in natural units, you just have h bar and c to the 1. And so then the formulas become a lot easier to write down. And also you make fewer mistakes, because if you've got to keep track of the h bars and the c's and the epsilon zeros and so forth, then that means that you're liable to lose track of the 2's and the pi's. And the 2's and the pi's are really important. In any event, this thing here boils down. So let's see. Maybe I should skip some of these steps and boil it down to you for you. Oh, I'm going to really boil it down. I'm skipping quite a few steps in the notes. We're down to 16 p cubed alpha. Oh, wait a minute. I don't want to go that far. There's actually an intermediate step here. 32. The energy of the final electron, the ejected electron, divided by its rest energy, mc squared. So that's a small number. Cp, which is the energy, which is sort of the. This would be the energy of the ejected electron if it were relativistic, but it isn't. But it's still sort of a mix. It's something, the units of energy, divided by the energy of the incoming photon. And then mc alpha over h bar. And actually I should, there's a nicer way of writing that, but I forgot what exactly we used on. So let me just go this way. A0 to the 5th sine squared theta over this big structure here. Let me see. Maybe let me back up one step, because I think this. Maybe this is a. Yeah, let me go down one step. Oh no, I think I'll stay with this step. Z to the 5th, A0 to the 5th, and then S squared plus Z squared over A0 squared to the 4. Okay, well. Yeah, actually, the step a little bit before that was actually slightly better. So I'm going to write it down in this form also. So another way of writing it is d sigma d omega is 32 A0 squared. This is this Bohr radius squared. Z to the 5th, EP over MC squared, CP over H bar omega K, sine squared theta over Z squared plus S squared A0 squared to the 4. I think this is actually the nicest way of writing it, because it tells you that the cross section here is roughly this area, the 4 radius squared. And then it's reduced by several factors. It's enhanced by z to the 5th. Remember, we decided it was so cheap, we just do it for an arbitrary charge on the nucleus. The energy of the ejected electron divided by its rest energy. The momentum of the emitted electron divided by, or not the momentum, the so to speak relativistic energy of the, it's not really that either. But anyway, Cp over h bar omega k, and then a geometrical factor sine squared theta. And then this is a good expression when S is not too big, because it gives us z squared plus s squared a0 squared to the 4th. In the other limit, when you're going to large S, then you want the s squared out there. And then in that limit, in other words, for higher energy initial photons, remember S is, where did I write it down? It's K minus Q over H bar, K minus P over H bar. Well, that's what it is, K minus Q, P over H bar. I don't see where I wrote it down. So in that higher energy limit, then the expression is 32 this ratio, that ratio, this structure, and then all these terms. I don't know. Anyway, that's how the cookie crumbles. Probably the simplest way of writing it is 16 p cubed alpha over m h bar squared omega k z to the 5th sine squared theta over e0 to the 5th s squared plus e squared over e0 squared to the 4th. Anyway, it's all in the notes and they're online. Now, this was when we averaged over the polarizations of the initial photon. Suppose the photon beam is polarized. And let's suppose that the polarization vector is epsilon 1, which we choose to lie in the point in the x direction. Okay? So if the initial photon is polarized in the x direction, then we have to substitute p squared over 2 sine squared theta has to be replaced by p dot epsilon r of k squared. And so that means that d sigma d omega is 32 p dot epsilon r of k squared p alpha z to the 5th over m h bar squared omega k a0 to the 5th s squared plus z squared over a0 squared to the 4th. Okay, so that's that expression, and now let's compute what this polarization E dot P is. So with these coordinates over here, we can see that epsilon is pointing this way, P is pointing that way. So what we're asking for is simply the x component of the momentum P. And so P dot epsilon r to k squared then is P squared sine squared theta cosine squared P. And so now we have d sigma d omega is 32 over m p cubed alpha over h bar squared omega k a0 to the 5th sine squared theta cosine squared p over s squared plus z squared over a0 squared to the 4th power. And remember, s squared is equal to k minus p over h bar squared, so that's k squared plus p squared over h bar squared minus 2 P dot K over H bar. And so that is K squared plus P squared over H bar squared minus 2pk over H bar cosine theta. So there's a cosine theta dependence in there. And that cosine theta dependence, I guess we can see that it's raised to the fourth power. So at higher energies, this can be, when K and P get pretty big, then this can overwhelm that. And that would mean that when cosine theta is 1, which is the forward direction, so it's peaked in the forward direction. All right, so that's enough of that. Of course, being peaked in the forward direction is what you'd expect physically if you didn't know anything about physics. You'd expect that if a photon of pretty high energy slams into a hydrogen atom, you'd expect that the photon, that the electron, the ejected electron, would go out more or less in the direction of the initial photon. And that's what this thing is telling us. Apart from the polarization, let's just check the polarization for a moment. It's saying that the polarization goes with cosine phi, and so that means that it's biggest when phi is equal to 0. So in other words, the peaking isn't, if the photon is polarized, the peaking isn't really that much in the forward direction, because you want it to be in the xz plane. So the peaking would somewhere be out like that, rather than strictly forward. And there's also, of course, this sine squared theta in the numerator. So that has the peaking in the opposite direction. That has the peaking out in the side direction. And that's dominant at low energies. At low energies, the photon, the ejected electron for unpolarized incident photons are basically in the xy plane. And the reason for that is that the electric field of the photon is perpendicular to its direction of motion. So the electron's kicked out to the side. Okay. All right, now, are there any questions? Because we're going to switch now to something else. All right, so let me do some erasing here. Okay, well, let's just recall our formulas for a general process. And let me talk about this process in a sort of, let's imagine that we have n photons of momentum k and wavelength k and polarization r. And we have two atomic states, A and B. And we're talking about equilibrium here. A goes to B plus a photon. Okay? All right. So the first process is Bn plus 1 S of T0 An, and this, as you know, it's going to be, and I'm working here in lowest order, so minus I over H bar integral 0 to t, it's b n plus 1 minus q over m p dot a n e to the I delta d t prime over h bar dt prime. And so this gives us IQ over h bar m, this factor, which is h bar over 2 epsilon 0 v omega k to the 1/2. And then we have b n plus 1. We have p dot epsilon. This is going to be an annihilation operator, a sub r of k, EDI k dot x, a n EDI delta e t prime over h bar. T prime, my writing is hell. And so this is IQ over h bar m, this square root, which you've seen so many times now. Now, the annihilation operator on the state n gives us a square root of n sub r of k. We're left with a matrix element. Oh, I'm sorry. This, did I do this right? A sub n goes to n plus 1. We need a creation operator here. And so this is, so a dagger on n is square root of n sub r of k plus 1 times b, and then everything cancels, and we get b, p dot epsilon e to the minus I k dot x a. And then an integral 0 to t, e to the I delta e t prime over h prime t prime. Okay. So that's the process for the process A goes to B plus gamma. And we can even think of this very generally. We can imagine A as being any old atom. It doesn't have to be hydrogen. And in that case, this B, we then have a sum over all the electrons. So it's P sub I e to the I k dot what is this? Which is xi. I guess it must be. Right. Right. Okay. So that's the expression. Now we want to compare that with the other process. And let me tell you, if you're doing this by yourself someday without a book, keep in mind that the initial state has n photons. Okay? So in a certain sense, this is a little bit misleading. So what we're going to be computing over here is A n minus 1 S T0 Bn. So in both initial states we have n photons. All right, well, this is going to be this is going to be very similar to that. It's going to be minus I over h bar this big square root, well, let's see, maybe I should go a little bit more slowly. Minus I over h bar, integral 0 to t, and t prime. You're going to have an e to the I, delta e t prime over h bar. And in each case, this delta e is going to be, maybe I should write down what delta e is here. Delta e here is EB minus EA, and it's EB plus h bar omega k, because there's an extra photon over there. Over here, delta E is going to be EA minus EB, and now there's an extra photon over here, so it's minus h bar omega k. And so you see, this delta E is just minus that delta E. And so that's not going to have any effect on it. And then the matrix element here is A n minus 1 sum over I pi dot epsilon r of k A r of k EBI k dot xi p n. Now the annihilation operator on an n photon state brings out the square root of n. And so this thing, I want to sort of write it in the same way. So this thing is I cube over h bar m, this factor here, h bar over 2 epsilon 0 v omega k to the 1/2. And then this will be square root of n sub r of k. And then it will be integral 0 to t. Well, let's see, wait a minute. I left out the matrix element. Let me put the matrix element in, because that's important. What's left is A, sum on I, pi dot epsilon r of k, EBI k dot xi e. And now integral 0 to t, EBI delta e, t prime over h bar, t prime. Okay. Now, these two things, you see, are very similar. They have the same square roots. They have the same overall factors. They have slightly different square roots of n's. They have a matrix element that's apparently different. And then they have time intervals. One is a complex conjugate of the other, because this delta is minus that delta. Okay, so it's obvious that they're almost the same apart from complex conjugation and so forth. And then the square roots. Let's look at this matrix element and see how far apart they are. Well, B times sum on I. So I'm doing this one. Pi dot epsilon. Let's see, did I get this right? There's a star here. Epsilon star e to the minus I k dot xi. Is that everything? Yes. A. So what is that? Well, that is A pi dot epsilon e I k dot x I b complex conjugate. Okay, so the complex conjugate of the matrix element, you switch the Gauss and Ketz, and you put the adjoint of the operator in here, and it just flips it around exactly the way we want. And this, of course, is the complex conjugate of the matrix element up here. So what we've got is that the absolute value, in other words, of the transition rate, that is to say, well, this let me just say b n plus 1 s t0 a n is equal to square root of n plus 1 over square root of n times the absolute value of a n minus 1 st0 en absolute value. So that's let me get a drink and then come back to this. So that's what we have. All right, now let's impose these conditions of equilibrium. We're imagining that we have these atoms and photons, and everything's in equilibrium, so we have a certain density of atoms in state A, a certain number of atoms, or density of atoms in state A and in state B, a certain number of photons in momentum K and polarization R. And it's that certain number which is the reason why we have the initial state n photons in both cases. So what is n of the number of atoms in state B over the number of atoms in state A? Well, we expect this to be the Boltzmann distribution, e to the minus EB over KT divided by e to the minus EA over KT. And this is then e to the EA minus EB over KT. Now, what is EA minus EB? Well, delta E is enforced to be 0 in these things, so EA minus EB is h bar omega k. So this ratio is E to the h bar omega over KT. So that's NB over NA. On the other hand, the equilibrium says that N of B times W absorption should be N of A times W emission. And so that, now we've seen that these two, now the rates are these things squared. And this one is absorption. No, that's emission. And this is absorption. Okay. So what we have is NB over NA is W emission over W absorption. Now if we look at it, W emission over W absorption then is N plus 1 over N. Good. On the other hand, NB over NA is E to the h bar omega over KT. And so now we have an exercise in high school algebra. N plus 1 is N, and just to make it easy, I'm just going to call this E. And so that means then that 1 is equal to N times E minus 1, and that means N is equal to 1 over E minus 1, or translating back into correct units, E to the h bar omega over kt minus 1. So this is what n sub r k is. So what we've derived then is the Planck distribution. And because these photons that have been so important in the last 40 or 50 years of cosmology, these were the photons that were around when the universe became transparent, something like 300,000 years after the last period of high temperature, which is called the Big Bang. So then with the redshift, they've gone from the temperature, the distribution for a temperature of maybe 10,000 degrees down to, redshifted down to something like 3 degrees Kelvin, 2.7. It's measured very accurately. Okay, you can, since we've gone this far, we might as well go the rest of the distance. The energy of the radiation field per unit volume in an angular frequency d omega is 1 over L cubed. That's the per unit volume. Then we're going to have h bar omega. That's the energy. This is the weight over e to the h bar omega over kt minus 1. There are two polarization states. That's 2. Then remember we have L cubed over L over 2 pi cubed gives us this this going from box quantization to continuum quantization, and then 4 pi k squared dk. All of that, if you put it together, is 8 pi h bar over c cubed, omega over 2 pi cubed, 1 over e to the h bar omega over kt minus 1 d omega. Or writing in new units, which is u of omega, d omega, d nu, it's 8 pi Planck's constant, nu cubed over c cubed, and again 1 over e to the h, whoop, that's not h bar, it's h. H nu over kt minus 1. Okay, so that's the derivation of all that. Any questions? Erase some of this and talk about the radiation from a charge. Radiation caused by a C-number current. In other words, real radiation, of course, is caused by electrons, well, any charged particle, and those charged particles described by a quantum field, and I suppose we'll have time to say what that is. In fact, I think that'll be the next topic after the scattering, Rayleigh and Rayleigh, because it's Rayleigh and Thomson scattering. After doing that, I think we'll switch to the quantized field. Anyway, as you know, this S of T0, this S operator, is a time-ordered product of e to the minus I over h bar integral 0 to t the interaction Hamiltonian, which is, so let me write dt prime, the interaction Hamiltonian, which is in our units. Actually, I do not have time to change the units here. So what I might do, if you just give me a break here, I'm going to write this as gamma, where gamma is a universal units conversion factor. So you pick your units and you stick in the right gamma. I'm going to do that for the moment. I think it's just simply 1 for SI, but it might involve U0. Okay, so that's our expression. And so in other words, canceling these two, we just have the expression like that. And now, throughout all the processes that we've been discussing here so far, we've been able to get away with first-order perturbation theory because we were talking about the absorption of one photon or the emission of one photon. And so we could take the e to the I h0 t prime over h bar, and instead of applying them to the operators in here, we can apply them to the final states, which are eigenstates of h0. Here we can't do that. And so what we're imagining is that this is a prescribed current. Prescribed current. It's a C number current. And this is the quantized electromagnetic field, but what we're talking about here is that A of x and t is e to the I h0 field t over h bar, or actually this is a t prime. But let me leave the prime off here. A of x and 0, e to the minus I h0 field t over h bar. And what that means is that this field is the sum over polarizations and wave vectors h bar over 2 epsilon 0 b omega k to the 1/2 epsilon r of k, a sub r of k, and now it's e to the I k dot x minus omega kt plus epsilon r star of k, a sub r adjoint of k, e to the minus I k dot x minus omega kt. All right, so that's what this field is here. It's this thing. The t dependence, it means that the operators have. I don't think that's AB H1 N1. I think it's an allergy stage. Let's hope. Anyway, so this is our expression here. Now, there's an identity which is important, very important in quantum optics. E to the A, e to the B is e to the A plus B plus a half the commutator of A with B. And this holds if, this isn't universal, this holds if A, AB equals 0 and B, AB equals 0. Otherwise, there's an infinite series here in the case. Okay. What does that mean? Well, up here, you see, we've got to time order these things. So this is not simply an exponential. It's a product. Oh, hey, I left something out. And this is d cubed x, of course. This isn't the field at one point. It's integrated over space. So it's the current density dotted into the electromagnetic field integrated over space. All right. So, and in fact, if we're talking about the integral from minus infinity to plus infinity, this would be integral minus infinity to plus infinity, d cubed x. This would be integral over all of space-time, I over h bar j dot a, with gamma for the arbitrary units. Okay, so what happens when you do these things? Well, you can take the e to the j dot a at one time. Let me just say x t plus dt times dt, and of course integrated d cubed x. In other words, this time ordered product, I'm just sort of writing it down. I over h bar is this. It's an infinite product, an ordered product of things that look like this. I over h bar integral d cubed x j of xt dot ax t dt. So the difference between here and here is that we move forward one time slice, dt. So this is the same as that. Okay? This is e to the a, and this is e to the b. The product of them is e to the a plus b plus a half the commutator. So this, in other words, is equal to e to the I over h bar integral d cubed x, and now it's j dot a xt plus j dot a of x t plus dt, all that times dt. It's the product of that plus something else, namely 1/2 the commutator, and now this will be integral d cubed x prime dt prime j prime a of xt a of x prime t plus dt, the commutator. But the commutator of a of t with a of t prime just involves commutators of a linear combination of a and a dagger with another linear combination of a and a dagger. And there you either get 0 or you get a constant. In any event, you get something that you get a commutator that commutes with a and b being just the electromagnetic field times j, effectively. So in other words, the upshot is that this whole integral here can be written as, well, I'm going to try to write it here, so I have to kneel down to do it. It can be written as e to the I over h bar integral d cubed x integral 0 to t dt prime j of x and t prime dot a of x and t prime plus a phase factor I phi. And the I phi is a complicated phase factor, and it's I think it's something that Glauber worked out. He published this in Phys Rev 84, number 3, page 395, and the year is 1951. Using these have been studied. And so, in other words, the S operator for prescribed current is the integral of J dot A plus a phase. And the phase is not physically important. And of course, I left out my camera. The units, arbitrary units. Now, one might not be impressed by this at first glance. It may look as though, well, we've taken something that was horribly complicated and we've reduced it to something that's merely complicated. But in fact, you guys have studied the coherent states at some point? Did Dunlap talk about coherent states in 521? Harmonic oscillator coherent states?
I'm not sure.
All right. I'm not either. All right. Well, it turns out that this operator here, this operator, if we look at it abstractly, it's an exponential of a linear combination of A and A dagger, a complex linear combination of A and A dagger, and in fact, it's also a unitary operator. It's unitary because J is real, A is Hermitian, and I is imaginary. IH bar gamma is imaginary. So this is a unitary operator. If you have an operator that's unitary and it's an exponential of a linear combination of A and A dagger, that's called a displacement operator. And for each mode, it looks like this. E to the alpha A dagger minus alpha star A. That's what this looks like. Because it's a linear combination of A and A dagger. Of course, it's summed over all modes and polarizations. So that's what you've got. But when that is applied to the vacuum, what you get is a coherent state. So let me call this, I'll use K, I'm suppressing the polarization index. So this turns out to be alpha, I can write alpha sub R of K. This is what's called a coherent state. And it has the remarkable property that A sub R of K on this coherent state alpha sub R of K is equal to alpha sub R of K times this state alpha sub R of K. In other words, the coherent state is an eigenstate of every annihilation operator with a complex eigenvalue. And so maybe I'll make this something related to this homework problem. Any questions about this? Now, I should add one word of caution. One word of caution. Well, maybe one paragraph of caution. In the real world, that is to say, as perceived by humans at normal temperature and pressure and so forth and so on, the electromagnetic field is essentially classical and, well, actually, in fact, that's not really true. But the electromagnetic field that one can make from simple objects like an antenna, running the current up and down the antenna and so forth, that sort of world is essentially classical, and in fact the black body world is in a certain sense essentially classical. That is to say, there are trillions of photons in any macroscopic signal, more than trillions, I mean, hundreds of trillions of the national debt in pennies. And each of them has a wavelength that's of the order of 500 nanometers or so. On the other hand, and so the electromagnetic field very often is almost classical. On the other hand, the world of well, I guess in this world, the current that's going up and down the antenna is also essentially classical. But there are many things that happen in our real world in which the electrons are individual electrons going around the individual nuclei, and so there the quantum aspect is more apparent than certainly more apparent than the field aspect. In any event, the bottom line is that if you make the current classical, keep the electromagnetic field quantized, compute the exact S operator, it is a displacement operator, which means that classical electric currents generate coherent states, which are eigenstates of the annihilation operators. And moreover, these states are the most classical states of the electromagnetic field. So in other words, the states that look most classical are the coherent states. And that sort of makes sense, because if you have an electric current that is completely classical, you expect that the corresponding electromagnetic field would be as classical as possible. And in fact it is. That's the coherent state. That's enough of this. Any questions? All right, why don't you cancel and end it?